This event is somewhat informal. Running a little late today. As I mentioned to Xavier, we don't have mochilas, we don't have little backpacks. Let's say Alberto Fest, we don't have little pens. The Alberto Fest, we don't do them either. Notebooks. But we don't need these things. We can simply enjoy what I expect to be great mathematics in a lovely atmosphere, Cuernavaca, which, as you know, always has ridiculously perfect weather. And, you know, just, I mean, we're here not for formal reasons, but here to appreciate and to show our appreciation and our admiration for Alberto Verjovsky, and that's what it's all about. So, that having been said, let me, without further delay, introduce our first speaker. He's Xavier Gómez Mont from from Guanajuato. He will speak about relations between Poincaré and Grothendieck. 2 hours.
First, I must say some things about Alberto. The first time I saw him, it was in the Congress in Puebla. He had just come back from his PhD, and so he gave this wonderful talk about Lyapunov exponents, and he finished completely full of shock because he was communicating the excitement. So he didn't communicate to me the understanding of Lyapunov exponents, but the love for Lyapunov exponents went in directly. So thank you very much. So I'll be speaking about some problem I have been working on for some time now, and which originated in some work I did with Alberto Verjovsky many years ago, and it has been deriving into the following situation. So we consider f a function from Rn plus 1 to R, real analytic, and with 0 and isolated singularity. And so this brings the following picture. So if we put f equals to x squared plus y squared minus c squared, so here we put the real numbers. Here we have a Rn plus 1, and so over 0 we have this cone, and then for some epsilon or minus epsilon, so we have something like this. And then on the other hand, something like this. This is small in the neighborhood of the origin. And so let's call this V minus and this V plus. And so the problem is to understand V plus and V minus say its topology or some other kind of structure that it has. So when we pass from the right and we're looking at the fibers of the map, something happens at the singular point, and we would like to develop algebraic machinery in terms of the function that will help to decide, for example, which homology groups appear on the right and which homology groups appear on the left, and what's the relation between the homology groups on the left and on the right. So there is this. This is the problem which is guiding my research. Now, so there's the following theorem by Arnold, which says the following, which says that the Euler characteristic of the fiber on the right or on the left is equal to 1 plus or minus sigma, where sigma is the Poincaré Hopf index of the gradient vector field, of the gradient of f. So this is partial of f with respect to C0, with x0. So the assumption that the function has an isolated singularity, this vector field, the gradient vector field, has an isolated singularity, and so we can compute the Poincaré Hopf index. So this means the following is that, so here we have the origin, we restrict the gradient vector field f, we divide by the norm of the gradient field, which goes from a small sphere of radius epsilon into the unit sphere, into the unit sphere in Rn plus 1, and the degree of this map is the definition of the Poincaré Hopf index of the vector field. And so the Poincaré Hopf index of the gradient vector field is containing information about the Euler-Poincaré characteristic of what's on the right and on the left. And I recall that the Euler-Poincaré characteristic is the sum of the, so this is also the sum of -1 to the j of the dimension of the homology groups of V plus or minus. So, so in some sense, this gradient vector field is containing this information. Now, in this example I did it on purpose, is that the Euler characteristic changes. The Euler characteristic is the cheapest topological invariant. Here, this is 2 disks, so this has Euler characteristic 2, and this is S1, so has Euler characteristic 0. So we are in a place where the Euler characteristic is changing. And then, in this sense, that's where the plus or minus sign appears. Now, for the proof of this, one uses a very simple idea, which is you morcify the function, morcify f. So what does that mean? That means that we're going to consider the function f epsilon, or let's say f delta for some delta x0, xn, and we're going to put the same f, and then we're going to put minus epsilon 0, and here we put a linear function. And so we put x0, so which make a linear change of coordinates, and consider just this epsilon 0, x0. And so this makes a small perturbation of the function f. And so if we compute the gradient of f delta, then it will be so partial of f with respect to x0 minus epsilon, and then the rest stays the same. So if we call this the set of points where this is equal to 0, gamma, this will be an algebraic curve. And for a generic choice of linear coordinate x0, this function will only have non-degenerate critical points. So it will be a Morse function. And so this means that this singularity that we had for the gradient of f, when we take the gradient of f epsilon, so this will break up into different singular points, but each one of each one of multiplicity 1. And so when we have a vector field, so the index of a vector field x at the point of multiplicity 1 is computed as the sign, and what we do is we take the derivative of x, we evaluate at the point P, and so that it has multiplicity 1 means that the determinant of the derivative of x at the point P is different from 0, and we take the sign. This we teach in calculus course. that now, so this means that for this point, some of these will come with a positive sign, and some other ones here come with a negative sign, and then one applies Morse theory to this, so that to this function f epsilon, and then one knows that at each point one is attaching a cell, and the homology that we are of the cell that we are attaching, it will be even if the sign is positive, and it will be negative if the sign is negative. And so this means that the change in homology when we pass through each critical point will depend on the Morse index, and then we put all this, so when the Morsification f delta goes to 0, all these points are coming in together at the same point. Okay? And then in the Morsification, we have the fiber over here and the fiber over here. So, and this is for the Morse function. So here, the fibers for some value, you know, on one of these extremes is the same as this one, and the other one is at this other extreme. So the idea of applying Morsification is, instead of doing a modification all at once, it is better to do a modification one by one and simple modification each time. And then if one can understand what is the change of Euler characteristics through each of these critical points, and then one gets all these together and one obtains this this result. So I mentioned about the proof because I'm going to be using this idea a little later on. And now there's a second ingredient. There's also a theorem by Eisenbud, Levin, Chimiashvili, which says the following thing. So let A be equal to, so here we put the ring of germs of real analytic functions on Rn plus 1, and we divide by the ideal generated by the partials. So here I am assuming that this is a finite dimensional ring. So this is a hypothesis a little bit stronger than the one I put here. They are called absolutely isolated singularities, which means that it's an isolated singularity when we view this as a function on Cn plus 1. So even on Cn plus 1 it's an isolated singularity. So this is this ring of analytic functions modulo the partial derivatives. And in here we have a preferred element, which is the class of the Hessian of f. So in the case of multiplicity 1, you take the Hessian of f and evaluate at the point. But if it's a degenerate critical point, if you take the Hessian of f and evaluate, you get 0. So you don't evaluate. What do? You take the class of the Hessian modulo the partial derivatives. So then this guy over here, the theorem says is that this guy is never 0. Is never 0. And if L is some function from A into R, which is sending the class of this Hessian of f to a positive number, one can construct the following bilinear form. From A cross times A into A. First, we do multiplication. Since this is a ring, we have the multiplication rule defined on A. And so this is, since this is a commutative algebra, so this gives a symmetric bilinear form. But in our courses of linear algebra, they taught us that you take bilinear forms valued in the field, not valued in an algebra, And so we continue with this L to get a mapping into real, to the real numbers. And so here we get
L is
this.
an algebra homomorphism? L is a homomorphism in algebras?
No, L is a linear map.
It's a linear map, okay.
So take any linear map, our linear map, and so in this form we get an honest bilinear form, real value. Now, this part of putting the L actually is psychological because we have this, they taught us this linear algebra course so strongly that, so we put it in, but it's not really essential. So you get this, and so the theorem says that this is a non-degenerate bilinear form, and its signature is equal to the Poincaré index of the gradient vector field of F. So this gives an algebraic procedure to compute the index. This is the generalization of this criterion of putting the sign of the Hessian of F at the point for non-degenerate critical point. So what this means is that when these points are converging to this point, then if you do the multiplication here, that since they are different points, then the matrix has just some things in the diagonals and 0. So this would be considered the similar algebra, but associated to the morsification. So you put this together as bilinear form, and then it turns out that when you tend epsilon to 0, then this converges. And here what's important is the word non-degenerate. You are converging to something which is non-degenerate, and the information contained in this bilinear form is the signature which is containing this Euler-Poincaré characteristic by this theorem of Arnold. So now the idea I have been following actually, so L, if you apply this L to some function G,
and by your definition of bilinear product, ED is really a Frobenius algebra, isn't it?
yeah, it's a Frobenius algebra. Yeah, so A would correspond to the moduli space of the F, and so this is the tangent space, and so this gives rise to a Frobenius algebra. Right. So and then just to see this, the word Grothendieck in the title, L of G, if G is some function, is 1 over 2 pi I to the n plus 1, the integral, and so here we put this partial of F with respect to Ci Ci equal to epsilon. So here we are in Cn plus 1. So we complexify the functions. We take, and here we're going to put G of C, dC0 exterior dCn divided by F, partial of F with respect to C0 times partial of F with respect to Cn. So this, it gives a linear function from Arn plus 1 to C. You plug in the function and you carry out this integral. This is a generalization of the Cauchy integral formula. Instead of taking a circle, you're taking a multi-circle. Here we're putting n plus 1 real conditions in an n plus 1 complex space. So this is an n plus 1 real dimensional thing. This is an n plus 1 differential form. We carry this out. This is independent of things here are holomorphic. Now, if G belongs to the ideal generated by the partials, then one by one we can cancel one of them, apply Stokes' theorem, then instead of taking this equal to epsilon, this is less than or equal to epsilon, it becomes a boundary, and so this integral is equal to 0, and so this means that this gives rise to a map which goes from A into C, so this algebra A, and if you do everything over the reals, then it goes over into the real numbers, and so Grothendieck's formula gives a specific L, and it satisfies this condition because if you apply an L to the Hessian, you get the degree of F. So, so that's why this is, and as I was mentioning, so all these are particular case of more general theorems, but I'm interested in this thing that this, so that's a Grothendieck residue entering in this fashion. Now, the idea I have been following is the following. I want to consider A, the linear map induced on the algebra A, induced by multiplication by F. So, here my only information is the F. From the F, I construct this algebra. With this algebra, I construct this guy. I construct this bilinear form. And I consider this map, and so this is an nilpotent map. So this means that F, let's say to the k plus 1 is equal to 0. So the class of F in the algebra A, some power will be 0, and so there is the following pyramid. I'm going to construct a pyramid using Jordan block decomposition. The only thing you have to know to understand what follows is Jordan block decomposition. So we want to apply to F Jordan block decomposition. So this means the following. So let's say something like this. Then we write something like this. Then we write something like this, and then we have something like this. So this means, and this is F. This you can apply this to any nilpotent thing. So here you consider the Jordan blocks of size 4, and then so here you put these primitive elements which are called, and then you push them, and then you go to 0. Here you put the ones of size 3, and the height of the pyramid depends on what is the number of blocks that you have. Then you have here the blocks of size 2 and then the blocks of size 1. Now, the thing about this F is that if I do the following, FA applied to B, this is equal to A, FB applied to L, because after all, this is L of FAB, and this is L of AFB. And this is a commutative algebra. So this means that multiplication by F is symmetric. Multiplication by F is symmetric with respect to that that bilinear form. And so, and then once one knows that multiplication by F is symmetric, this means that we may decompose the algebra, the bilinear form further. And so here the claim is the following, is that there exists, one may choose basis for this algebra A in such a way that the bilinear form L will have a orthogonal decomposition, and here, so I'm going to put it like this. This part I'm going to call primitive 1, this is primitive 2, this is primitive 4, and so, so first we have that the algebra A decomposes as the direct sum, and so we have Fj of the primitive I, and so I goes from 1 up to k, and then the j goes from 1 up to I. this means that, so using this Jordan block decomposition, one gets this thing, and then one may choose a basis in such a way that what happens here is that in the non-orthogonal parts, we take this one, and it's symmetric one with respect to this triangle on the same level. So we can choose a basis in such a way that we have an orthogonal direct sum decomposition, and the only parts which are non-orthogonal is this one with respect to this one. This one with respect to itself will be orthogonal, but it is this one with respect to its symmetric one. Now, so that's just a little linear algebra to prove this. Now, once one has this, then also another remark here is that when you do something like this, then the bilinear product looks 0. Here you have some q, here you have some q, and here you have 0. But the bilinear forms which have this form always have index 0. Okay, so it's not difficult to prove that the bilinear forms have index. This index have signature 0, and so this means that in this product, the only ones which contribute to the signature of the bilinear form are the ones in the middle, and only appears for the even dimensional ones. So when you put these two extremes, these on the level of signature, they cancel out. So for example, for 3, so this means that here for 2, if you have 2, then these two, they cancel out. This one cancels out with this one cancels out with this one, and so the only non-trivial terms are the ones which correspond to this middle and the odd dimensional ones. So this means that in this signature, we are repeating many times, so on every one of these platforms. So the thing why this works is the following. See, if I take something here and something here, and I want to do product, then I say, well, look, this one comes from someone, and so I pass this one to this other one, but then this one I push with the F, and then it goes overboard. So this means that A and B, you can lend F's one to the other. But in this pyramid, if you are very close to the end of the pyramid, if they push you over, and then it becomes 0. And so in that sense, that's why these orthogonality properties function. And so in particular here, so this means that this bilinear form decomposes into a direct sum of many times the same primitive forms, and then all the ones which are even cancel out for the question of signature, and only the ones which are odd appear in the signature of the A, of this A. Consider just this part, just to get the primitive ones. This is the annihilator of F. So this is the kernel of F. These are the ones, when you apply F, they go to 0 in here. And now in here, we can consider the following bilinear forms. Fj restricted, or let's say here, to this, so what I want to understand is these bilinear forms. Fj restricted to the annihilator of A of F intersection with Fj minus 1. So cross this into R. So these are degenerate bilinear forms. Forms with signature sigma j. So in some sense, these sigma j's are more elementary pieces than this sigma over here, and in particular, sigma is equal to sigma 1 plus sigma 3 plus sigma 5 plus whatever. So in this signature here, which is containing this topological information, only the summation of the odd signatures appear, but there are more primitive, there's a more primitive information which is contained in these sigma j's. So here the problem is what is the topological meaning of these sigma j's. So this is the question I want to address. So in some sense, so we have a question about the Euler characteristic. This Arnold theorem, it says this is related to this signature, to this bilinear form. This bilinear form, you may decompose it further into pieces. You have some elementary pieces. You can understand the bilinear form here from these elementary pieces. And so one can ask, what is the Arnold theorem, but not related with the full signature, but for each of these signatures that we have over here. So that's what we are trying to understand. So we have this precise algebraic bilinear forms, which computations can be carried out in the computer for these bilinear forms. And so we are trying to understand what is the topological meaning. So it should be a finer. So to try to understand this, that's where I pass to this Poincaré duality. And so one first idea is extend everything to the complex numbers. So we have Cn plus 1 into C, we have F, and so the picture now changes in the sense that we have here, so let's say Fc, so this would be V epsilon C, which would be now the points with Cn plus 1 in such a way that F of Z is equal to epsilon. So this is the Milnor fiber. The Milnor fiber. Here we have the singularity V0C. And now here the game here is to go around the loop. So here the topological situation is simpler in the sense that the only interesting cohomology group of this V epsilon, the complex one, is the N, and then this is equal to, if we use complex coefficients or real coefficients, let's say complex C to the mu, where mu is the dimension of this algebra A. So A, as before, is, well, now called AC. AC is germs of holomorphic functions divided by the partial derivatives. So it's again this finite dimensional algebra. Mu is its dimension, and so this has cohomology only at these levels. And then the interesting map here is the monodromy map T, which is the monodromy map which says how the nth cohomology groups, when you go around the singularity, how they transform. And so by the monodromy theorem, it is known that this T has eigenvalue roots of unity, and that the size of the Jordan blocks are bounded by n plus 1. And so that's relating this to these Jordan blocks. And then we are going to decompose T into its semi-simple part times its unipotent part. So any linear map can be decomposed with semi-simple and its unipotent part. Here we have the eigenvalues, and here we have the information of the Jordan blocks usually one centers information on this semi-simple part, but here, and we're going to consider n is equal to 1 over 2 pi I, the logarithm of tu. So we're going to take, I'm sorry, tu minus the identity. So tu has only eigenvalues 1. Tu minus the identity is nilpotent. And so this logarithm is just some power series. But since it's nilpotent, this is really polynomial in T of u. And so that's this map. What we are, so we want to find the relation between multiplication by f in this local algebra and multiplication and composition with n in the cohomology. So this n is a map which goes from Hn p epsilon c into itself. It's an nilpotent map. Now, we're going to do the following thing. So this was a germ of a holomorphic function, and so we make a small perturbation of the function in such a way that the singularity is analytically the same. We don't change the analytic type of the singularity, but f now is a polynomial. So we can assume without loss of generality that f is a polynomial, and not only that f is a polynomial, but that its extension at infinity is smooth. So what I'm saying, I want to think of this as part of a compact, smooth, compact manifold. And in this case, so let's call this, so we have Hn v epsilon bar c. So this would denote this compactification into a compact complex manifold. And here we have Hn of v epsilon c into c. And so here we have coproduct and integrating over the fundamental cycle. So we also have here a non-degenerate, so Poincaré duality then asserts that this is a non-degenerate bilinear form. Now, the monodromy that I have here at the germ, in the compactification, it's just going to be the identity. So this means that the thing I added here at infinity is going to, everything is going to be in the semi-simple part, because in that part is the identity. Monodromy is the identity. So they have the same unipotent part, and so now you start seeing the relation. Here we have A with a non-degenerate bilinear form by Grothendieck duality. We have multiplication by F, which is a nilpotent operator, and on the other hand here we have so this also has the property that if we do this alpha and beta with respect to this Poincaré duality, this is also equal to T of alpha and T of beta. So this means that the monodromy map is an automorphism of the bilinear form, So, and so the question is, how do you relate the two? How does one see, and in here we can obtain the following forms. You can do, how about doing nj alpha and then beta? So this is going to be some bilinear form where instead of doing alpha with beta, you take alpha, you apply n j times, and then you couple with beta, and then you get this bilinear form in the cohomology. Okay, and so what we are searching for is for a relation between these bilinear forms which have this algebraic definition and are computable in using standard programs, and this product which is which comes from the monodromy. So now in this sense the result we have is phrased in the following form. So here we have our puncture disk. Here we have this fiber. And so we have, this is F, so we have the union of all the cohomology groups of these VT complex coefficients with T over the puncture disk. So this becomes a fiber bundle, a vector bundle over the puncture disk, and then we have the sheaf of sections. So let's call this H. So we have the sheaf of holomorphic sections of H times the sheaf of holomorphic functions of H. As sheaves, and here we can do this this coproduct and integrate over the fundamental side. So this means that I explained that you have a product in one. You don't only have a product in one. You have a product in each one of these vectors, in this vector bundle, because on each one you apply this coproduct. So you obtain this, and so this goes to holomorphic functions. Now, if here instead of putting holomorphic functions, we put multiple valued holomorphic functions, multiple valued holomorphic functions. So it would do like this. But now, if we put multiple valued holomorphic functions which correspond to the monodromy representation, which means that when you come back, you don't, so not holomorphic functions, but multi-valued holomorphic functions, but when you go around the disk, you come back not to the same cohomology class, but to T of the cohomology class, or in covariant with respect to the monodromy map. Then, when you do the coproduct, since this is invariant under the T, this will go not to multi-valued functions, but really to functions. So in that sense, we want to do Poincaré coproduct, but not for one, but for families. Now, where do we get these functions? These sections. So these are sections of this bundle. So one way to do this is to take omega n of Cn plus 1. So if I take an ambient n form, every time I restrict it to a fiber, it becomes a holomorphic n form in Cn plus 1. So if I take omega here, if I take the class of omega restricted to Vt, this will give me a holomorphic differential form of top class. And so I can take it, it will be a closed form, and so I can take its cohomology class in Hn of Vtc. So this means that if I am giving an n form in the global space in Cn plus 1, I restrict to a fiber, it gives me a cohomology class, and so when I move the omega, so when I move the T, this will give me a section of this bundle. So this is a way to obtain a section. Now, there's a smarter way, instead of doing it with n forms, is you do it with n plus 1 forms. But now the trick is you take here some eta, but now this eta you do some process which is called, you divide by df. So here we have an n plus 1 form. You divide by df and restrict to Vt, and it also will give you a section of this form. And so, in this manner, we can obtain So in this manner, we're going to obtain from omega n plus 1 forms in Cn plus 1, 0, cross omega n plus 1, Cn plus 1, 0. So we take here an eta 0 and eta 1. And so we first do eta 0 divided by df and eta 1 divided by df. And then we do this process. Let's call this S of omega. So and then, so let's see, and then let's see, and then we want to do the product. Then we want to do co-product of these two, eta dot df, co-product eta 1 df, and so, and this will give a holomorphic function in Cn plus 1, 0, and so this gives a map which goes like this, Cn plus 1. So this map is you take two forms, two global forms, you construct from these corresponding n forms, then you take its classes, its S classes, and then you do co-product, you integrate over M, and now you get a honest function, and so this gives this map over here, and so this map has the following properties, is that its image is contained in the ideal generated by, so here, I'm sorry, so this is O of T, I'm sorry, this is O of T, so this is because this now depends on T, so this is a multiple of T to the n plus 1, so this is contained in here, and so if you divide by Tn plus 1, so the theorem is the following. So this is La Rosa, this good of mine, which says is the following. So if you consider 1 over Tn plus 1, this map, let's call this map phi, which goes from omega n plus 1 cross omega n plus 1 into O. Now here we're going to divide by the partial derivative, partial of f0, partial of f with respect to Cn. And here we have, so this also descends to a map from omega n plus 1, and then this is df exterior omega n plus omega n plus 1 df exterior omega n. So the claim is the following, is that, so usually one is used that the residue is the polar part. But here in this one, this does not have a polar part. It's always vanishing when you approach 0. So if you take the principal non-zero term, this would be the coefficients in n plus 1. And so that's why we're taking the coefficient in this. But then we're taking modulo the partial derivatives, and so this gives this algebra A. Now, so this map is take this function, this modulo the partial derivatives. Now observe that if you consider df exterior omega n, this goes to 0, this goes to 0 too, and so this is giving a map which goes from A cross A into A. And so this is this Poincaré residue map. This is Poincaré bilinear form, the one over there. I'm sorry. So this so let me see. So this is, so we're obtaining this map here, right? So this is and so the theorem here is that this map that we're obtaining here is Grothendieck residue. This is Grothendieck residue. So we are obtaining Grothendieck residue as a residue of doing co-product in using Poincaré duality. And the second part is the relation with this Fj. So now if we take eta 0, eta 1, and then we apply Nj to S of eta 0 and S of eta 1, then the residue, which is this process of sending to its class and observing that this vanishes over here, so then this the residue of this bilinear form is equal to this bilinear form I'm interested in understanding. So this, we're trying to figure out what is a topological meaning of some algebraic form. So this is the algebraic form. What we have found so far is that there is this connection between the bilinear forms obtained by multiplication by f to some powers in the local algebra and the bilinear forms we obtain on the cohomology of the compactified Milnor fiber when we do coproduct, and the role which is being played by multiplication by f is being played by composing with this transformation n, which is the logarithm of the unipotent part of the monodrome. And we hope to continue and obtain more information. That's it. Thank you.
Preguntas, questions?
Multiplication by f is symmetric with respect with the linear form of but in this case it's also symmetric with respect to
Right. So in this case, it's going to be symmetric, and sometimes it's going to be anti-symmetric depending on the dimension. And so actually, that's a part of the difficulty here is the following: is that so here I should have put partial with respect to t, and think of this as a d module. And so once you so this means that here is going to come, so you have this tn plus 1, and then you have something, and then here comes a partial with respect to t, this n plus 1, and then it turns out that once you put in this, in the case when it's anti-symmetric, once you consider it as a d module, then it becomes symmetric, and so I did skip that part. So to really make all this fit, you have to understand the d module structure, and so the d module structure here comes from the connection, from the Gauss-Manning connection. So you have this Gauss-Manning connection on this part, and so to finish formalizing this idea of residue, one has to think of it as a d module. So if you think it of as a d module, it fixes the sign.
See, that was the question I wanted to make. That obviously, the Gauss-Manning connection is there. Because you have this canonical bundle is considered by Gus Bunny, no?
Yeah, that's
So the connection must play a role, and that's the answer you answered.
Yeah, well, here I mean, what we're looking is the unipotent part, so the unipotent part of the monodromy of the connection.
Of the monodromy of the connection. It's a flat connection.
Just a little comment is that this all seems very closely related, and maybe it could be slightly streamlined if put in the language of Frobenius manifolds. And that would suggest further that if you are in the case of a particular Landau input model, then you could translate with mirror symmetry to the Calabi-Yau case the same sort of structure for the which would be very interesting, because you would have on the other side as well a relation to algebraic invariant.
Other questions? Okay, well, I recommend we reconvene in about 10 minutes. The next round.